This project has been developed together with my colleague Eduardo Villa. It's out with us today. We work in the Laboratory of Electronic Instrumentation for Space Systems in a multidisciplinary team that develop also other projects for satellites and space systems, and all with the support of Dr. Saavedra that are present with us today. And well, currently I'm working on my thesis of the topic that I want to share with us today. Solar simulator for nanosatellites. It's about the development of a simulator for nano, micro, and lower categories of satellites. And to understand better what is a solar simulator, I want to introduce you with this little background. Solar simulator is an instrument whose function is to provide visible electromagnetic spectrum and also irradiance as close as possible to the sun, applying different lighting technologies and techniques to achieve this goal. Solar simulators have become very important because they give us an estimate of the performance of the photovoltaic panels that we use in our satellites during the period of orbit, of course. Nowadays, most of the simulators that we have in the market functions only with a diagonal light source and a fixed test plate, and only few of them can generate a partial shading. As we can see, we have here simulators that I have mentioned only with a fixed test plate. And to understand better what is the behavior of the irradiance, I will play this little animation. For example, we have here low Earth orbit. We have also the level of irradiance. And when the satellites are around the Earth, we can see that the irradiance varies. And when we are in a low altitude, these effects of the irradiance is very high. But when we're in a higher altitude, we have not this high dynamic because the presence of the Earth don't affect the effect of the irradiance. And for develop a solar simulator, we need to know a little bit of standards and other concepts that help us to put the simulator as close as possible to the reality of the sun. We need to know about three core standards. They are spectral match, non-uniformity, and temporal stability. The first standard means the coverage that has our light source versus the electromagnetic spectrum that emits the sun. For example, we have here the electromagnetic spectrum of the sun, and versus there we have a halogen lamp. And we can see here that the electromagnetic spectrum that emits the sun is not enough to cover all the electromagnetic spectrum that have the sun. And this is the reason because we need to know about lighting technologies that covers as close as possible the electromagnetic spectrum of the sun. The second standard is about the non-uniformity, and that means that the irradiance that the light source emits must be the same in all the plane. For example, we have here one light source, and when we turn on, we can see that all the irradiance that we have is concentrated in the middle of the plane, and that is bad for the simulation because it's not a real case what's happening in space. And to get this better, we make an array of lamps, and when we turn on, we can see that the irradiance that has the light source is better, and we can say that the irradiance is the same in all the test planes. And the last standard is the temporal stability. Temporal stability means the variation of irradiance that we have during the period of simulation. When we fix or determine a certain level of irradiance, we must be to have this level on all the period of simulation. As we can see, for example, in this graphic, we have a little variation in this time of simulation, and as lower is this variation, as better is the light source. Also, About the standards, we need to know important concept called IAM conditions. This concept is used, for example, the companies that develop photovoltaic cells, because when the company says our photovoltaic cells, they use these conditions to test that the photovoltaic panels works correctly. For example, when I say that I have an IM1 condition, that means that I have a level of irradiance of 1040 watts per square meter, because I have the irradiance on the I have the sun on the zenith, and I'm inside of the atmosphere, because this is the number of, this is the reason that I have a 1. The next case, for example, was zero conditions. In this condition, I am outside of the atmosphere, and at this level, the irradiance is more. We have here 1,353 watts per square meter, but also is the sun on the zenith. Another case where the IM 1.5 condition, we have here an angle between the zenith and the angle of irradiance of 48.2, and at this level the radiance reduced because the irradiance comes not directly to the panel, and that affects the energy that receives the photovoltaic panel. And last case was the IM2 conditions, where the angle is bigger. We have an angle of 60.1, and here we can see also reduce the final irradiance. We have here, for example, an irradiance of 8040 watts per square meter. And knowing these concepts, we can start to develop the simulator. But before we start, we need to have goals to give a direction to this project. These goals are to propose a dynamic solar simulator. Also, the simulator must be capable to simulate different orbits. Also, the simulator must be measure different parameters like voltage, current, irradiance, and temperature. And the last goal was to generate partial shading and to design a low-cost simulator. And to start to design a simulator, we need to analyze several mechanical structures, and also to analyze very how comports this phenomenon of the irradiance. And the end result of this investigation was to develop a simulator that has the capability to move the distance between the test plane where we put our photovoltaic panel, and also a fixed light source. I will prefer to show you how to function this. We have, for example, here a test plane, and when the distance between the light source and the lights are very closer, the irradiance is more. And also the effect of partial shading is by adding to the test plane angular motion, and when we turn this angle, the level of irradiance, of course, is reduced. After proposing the motion that will have the simulator, we need to determine the light source. And when we determine the test plane, that also means that determine the light source, because the light source must cover all the test plane. And to achieve this, we need to know about lighting technologies and its characteristics. For example, we propose a spectrum that covers as close as possible the spectrum of the sun. For example, we propose four lamps. We have a cool white LED lamp, also a halogen lamp, a plasma lamp, and a metal halide lamp. And when we put together all these lamps, we have an end result of a spectrum. You can see here. The end spectrum is the sum of all spectrum that emits the lamp. This spectrum is not enough to cover all the spectrum. You can see here that we have some areas where the lamps not covered enough, or this the the actual technologies that we have in the market. And also the irradiance is important. For example, when we want more irradiance, it's equal to the number of lamps that we have in our array of the light source. If we have more power, and this means also more irradiance. And the important point of the light source is, when you can saw in the past slide, is that we use incandescent lamps, and these types of lamps, many of the energy that used to generate the light is also used to generate the heat, and this heat affects the simulation because it reduces the performance of the photovoltaic panels. If you can see here, when we not do anything to reduce this temperature, the heat of the test plane going up, and that affects the simulation. For this, we have a cooling system that reduces the temperature of the test plane. It's many forms to reduce the temperature. For example, we make an array of fans that makes that the wind reduce the temperature of the test plane.